Oh, by the way, so what did people think about the midterm?
It was definitely challenging for like 2 days. It took a lot of time, at least for me.
I might have made it a bit too long. I will admit that. I didn't cover absolutely every single type of question, but on the assignments, I basically covered every single type of question once. And then if I did that for every type of problem, the midterm would be the length of 2 assignments. So I should have perhaps considered dropping some topics because after I said it, I'm like, okay, this is a good exam. And then I sort of thought that it might be too long. So I think that's might be an accurate criticism. Anyone else? So the question is midterm thoughts.
Oh, the last part of the last question was pretty long.
So the inhomogeneous system where you actually had to invert a 3x3 matrix. Yes. There was also one problem, which was a multiplicity 3 eigenvalue, which had only one eigenvector. And if you actually looked at the equation, the first one said x prime is some multiple of x. So you could have reduced it and then installed a 2x2 system that was inhomogeneous. That was one way to do it. But if you did it the intended way, then that would go. But yeah, I agree. Probably the inhomogeneous one was longer.
For the x prime equals 4x1, I think what I did there was I just did substitution.
So did you solve the first equation for the x prime equals for x1? You mean the system that had that as one of its lines, right?
Yeah, I solved the thing for x and then plugged that in for z and then did that for y.
Yeah, I did the same thing for that question.
So
Yeah,
I should have probably chosen a different matrix to multiply it by, because how I wrote that problem myself. What I did is I started with, I guess, the matrix something like 4, 1, 4, 1, 4, 0, 0. I think it was 4s along the diagonal. It might have been 2s along the diagonal, one or the other. Was it 4s or 2s? What was the eigenvalue?
4s.
4.
Okay.
Oh, and 1, 2. Oh, I see. Oh.
And wait, there should have been multiplicity 3, right? With 4s?
And oh, there was one on the there was an of the lower left was a 2. Oh wait, no, never mind.
Oh, well, no. Yeah, that's I took this matrix and then I multiplied it by some matrix A and A inverse in order to get that one. So that's how that works. Because then basically the sort of generalized eigenvectors would have been the columns of A. But what happened was when I did this, the top row only had a single non-zero entry or something along the lines of that. And that sort of enabled a shortcut solution, which is the one that you mentioned you did, which is solving that equation first. And I sort of realized that this was a possibility. And I said, like, whatever, if you do the shortcut method, then you've done the shortcut methods. Good for you. But yeah, the problem started off by just like explicitly constructing something that only has one eigenvector and then conjugating it in order to get another matrix. Right. So it turns out that applications are hard. So most of the lecture today is actually going to be me solving problems live because I spent 4 hours and then I did not like produce notes. I only have 1 page of notes, which is bad. So we're going to do it live. So we're going to get to circuits in a bit, but first we're just going to analyze basically different kinds of second order motion. So we are going to be looking at one particular equation. And the equation, it's going to be given in terms of t. So And then I'm going to write this coefficient as 2r. And then plus omega naught squared x is equal to sum of t. So okay, the differential equation is going to be x and sometimes it's going to be y, but anyway, x is a function of t. So this is our equation. And there are going to be several cases of this. So we refer to the cases as, so let's say case alpha is the case when both r and f are 0, and you just have the equation x prime prime plus omega naught squared x is equal to 0. And this is known as free undamped motion. And here we're going to assume that r is greater than 0. Or greater than or equal to, rather. Case beta is going to be the case where we have a non-zero function f, and this will be known as a forcing function. So this is forced damped motion. Sorry, undamped motion. Case gamma is the case where we have this resistance term, or it's called a damping term. Sorry, 2rx prime. And this is free damped motion. And then the most general case is going to be forced damped motion. And we're going to look at, in this analysis, at forcing functions of very specific forms, specifically oscillatory forcing functions. So in the first case, let's see what happens. And this is, so it's free undamped motion, aka simple harmonic motion. So in this case, our differential equation is of the form x prime prime plus omega naught squared x is equal to 0. And so this has an associated characteristic equation, which is lambda squared plus omega naught squared is equal to 0. And so we get that lambda is equal to plus or minus I omega naughts. And then looking at our prescription for solving constant coefficient homogeneous linear equations, the solutions that we'd get would be the two fundamental ones: cosine omega naught t and sine omega naught t. So we can write A as A cosine omega naught t plus B sine omega naught t. And what we can do further is we can take this and we can factor out the square root of A squared plus B squared. And what does doing this accomplish?
It like normalizes it.
Yeah, so in particular, A comma, the point, where would it lie?
A comma B. Oh, that would lie on the circle.
Yeah, on the unit circle. So in particular, there's some angle on which it is on the circle. And so we're able to find some angle, let's say delta, such that this is cosine delta and this is sine delta. Now, what's going to happen is, so for for cosine of, let's say, delta is equal to A over root A squared plus B squared. And for sine delta is equal to B over square root A squared plus B squared. So what would happen if we sort of think of the graph of tan? It looks like this. And arctan looks like this. And if we sort of think about it, then what's happening is that arctan takes values between minus pi over 2 and pi over 2. So what happens basically is if you have the unit circle and you sort of have a specific ratio A divided by B. So this is M is equal to, let's say, B divided by A. Then what's going to happen is that arctan of B over A is going to give you an angle between pi over 2 and negative pi over 2. And that corresponds to the case when A is strictly greater than 0, right? So for A is greater than 0, delta is equal to arctan B over A. And then if A is 0, then we can get the value either pi over 2 or minus pi over 2, depending on the sign of B. And if A is less than 0, then we sort of have to flip this and take angles in this range. So the formula for delta isn't important. What's important basically is that giving cosine of some angle and sine of some angle uniquely defines the angle on the unit circle, because these are the coordinates of the point on the unit circle. So it uniquely defines the angle up to an additive factor of 2 pi. So delta can be found. And if A is greater than 0, delta is this specifically. But then if we have cos delta cos omega naught t plus sine delta sine omega naught t, what is that equal to?
It's cos lambda minus W0t.
Minus. Wait. Yeah, it minus. Let's good. That's good. Let's keep this term positive and make delta negative. And the reason for this is, how do you remember these formulas. So now I'm going to do an aside before I actually do this. So we know, for example, that e to the I theta is equal to cos theta plus I sine theta. So if you have e to the I alpha plus beta, then that's equal to cos alpha plus I sine alpha times cos beta plus I sine beta. So what happens then is that this is also equal to cosine of alpha plus beta plus I sine alpha plus beta. So if you equate real parts, then when you multiply the two signs together, the I squares give a -1. So that implies that cosine of alpha plus beta actually introduces a minus sign on the sine cross terms. But we don't have a minus sign there. So it's actually the cosine subtraction formula that we're applying. And by the way, so every single addition formula, double angle formula, etc., you remember just by doing this in your head. Like I don't have these formulas memorized, I just do them in my head every time. It's you only need to know one thing, which is this, and then you can write out the formula. So this becomes square root a squared plus b squared times cosine of omega naught t minus delta. Okay, now in general, the solution can also be written as, so replacing a squared plus b squared with c and then replacing delta with minus delta. You can introduce two new coefficients. So I'd like to keep a positive sign there. I'm just redefining what the coefficients are, but that gives me sort of the general solution. So what this looks like is that it's just oscillation, except that it's shifted. So what C is the amplitude. Then delta is the phase. So those are the names of these things. Then what we have is two other quantities. We can consider T, which is 2 pi over omega naught. Is the periods. So if T is measured in seconds, this would be how many seconds does it take to go around once? In other words, it's measured in seconds. If T is measured in seconds, it's measured in the same unit as time. And sort of 1 over T, which is the question of how many times do you go around in a given unit of time. This is known as, so it's omega naught over 2 pi, is the frequency. So let's see an example of where this arises. So what we're going to do is we're going to assume that we have a spring. And we are going to assume that when the spring is just sitting there, it has height, which is going to be L naught. Then what we're going to do is we're going to take the spring and we're going to attach a mass to the end of it. And that's sort of going to pull the spring down because the mass is heavy. And what that's going to do is it's going to be as stretched as it is before plus a bit more. So if I draw this line here, I have L naughts, and then I also have an additional stretching L. And I'm going to take this point, and I'm going to use this as y equals 0. And I'm going to keep my positive y direction in this way. So what's going to happen is that if I take the spring and I stretch it even further, then the measurements are going to be, this is going to be y, however long this is. And if it's in this direction, then it's going to be positive, and otherwise it's going to be negative. This is L and this is L naughts. So how do things work? Well, there's gravity. Well, so first off, how does physics work? There's Newton's equation, or second law. And what this says is that there's something called force, and force is equal to mass times acceleration. So force is going to have units meters per kilogram meters per second squared. If it's measured in newtons. A newton is a kilogram meter per second squared. Now, acceleration we can write as being the second derivative of position. So this is equal to m d squared y dt squared. Now, so the question is, what is the force? Well, there are formulas for what the force is in terms of things. So gravity is a force that acts in proportion to what's the weight of an object is, or rather what the mass of an object is. Weight is a unit of force. So gravity has a force of mg, where g is the gravitational constant, and it's about equal to 10 in meters per second squared. It is a unit of acceleration. So g represents the acceleration that an object would experience on the surface of the Earth, independent of what this mass is. And then we have the spring force, which is the displacement. And the spring force is proportional to how much it's displaced. So in this case, it'll be in the opposite direction of displacement. So it'll be negative. Then there's a spring coefficient, which is usually denoted by K, and then times the displacements. And in our case, the displacement is going to be L plus Y. Because that is how much it has moved from its equilibrium unweighted position. Now, what happens is that in the equilibrium position, there's no acceleration. It's just going to sit there. So in that situation, the force has to be 0. So at equilibrium, we have A is equal to 0, which implies that F is equal to 0, which tells us that if we take the sum of these two forces, mg. Now, at equilibrium position, by default, the value of y is defined to be 0. That's our reference range for y. So mg minus, that's taking the sum of forces, k L, and then y is 0 is equal to 0. So that tells us that mg equals KL. Now, in general, so we have that force, which is, well, rather, MA is equal to all the sum of the forces. And so the sum of the forces are mg and then minus k L plus y. Now, what that's equal to is mg minus kl minus ky, and then I'm going to bracket this term, and this term we found to be 0, right? So basically, in the presence of gravity, all that happens is that the spring sort of default state changes from being a distance L to being distance L plus L naught, and then you can forget about gravity. It's equivalent to a system in which there's no gravity at all, and the spring is just sitting at this level. So basically, gravity cancels out and we can forget about it. And so what happens then is that d squared y dt squared is, well, rather, let's move this term over and divide by m plus k over m y is equal to 0. And so the solutions are going to be and k is always going to be greater than 0 because it counteracts the displacements. So, and mass is also going to be greater than or equal to 0 because we don't have negative masses. So k comma m are greater than or equal to 0. Well, m is strictly greater than 0, or else we're dividing by 0. In this case, let's say k and m are both strictly greater than 0. That's what we want. Then, because we get different solutions in the case where k equals 0. Then it would sort of just the spring wouldn't matter. If the spring constant were 0, then we could imagine if the spring was just not there. Although okay, anyway, k is greater than 0. So the solutions are going to be y is equal to some amplitude c times cosine of square root k over m t plus delta. And basically c and delta are going to depend on where the spring is initially at time 0. And I guess also what its velocity is at time 0, because this is a second order equation. So we'd sort of give both the position and the velocity, and those two initial conditions would correspond to these two parameters in the general family of solutions. Now, there's another type of equation where we sort of get this type of motion coming from, and that's from a pendulum. Although we'll see that it's not exactly the case that you have this type of differential equation. It's only an approximation that you get this type of differential equation. And so what a pendulum looks like is, okay, you have some ceiling, and then you have something, and then at the center of its mass, you have a thing right here. And this thing has mass m. And so it's going to be at some angle theta. And so we can imagine that gravity is acting from the center of mass of the object. And that's going to be a force of magnitude mg. But then this force can be divided into being in two directions. So if we drop a right angle here, then we can decompose this into two orthogonal vectors. And what happens is that if we just look at what the angles are, we can sort of imagine extending this angle, this line further, and then you have two parallel lines here. And so this angle is equal to that angle. So this is theta. But then you have this line and this line, so this is theta. Which means that this thing right here is going to be have magnitude mg sine theta. And then this thing right here is going to have magnitude mg cos theta. Now, this string is sort of rigid, which means that if there's force in this direction pulling directly against it, then its rigidness will just cancel that out. So the only actual force acting on the object overall is this centripetal force right here. So the centripetal force is this. And sort of if we make the direction positive and we make theta be positive in this direction, then sort of on this plane, let's make the positive direction actually be this is the positive direction, with depending on what the angle is. Then it counteracts. So if theta is positive, this will be negative. So it's instantaneous movement along this centripetal axis. So if we set at instantaneously this to be this, then we'll have MA, which is equal to M, let's say d velocity dt, measured along this axis, is equal to negative mg sine theta. Now, what happens is if we sort of think of position along here, if we say, then we can sort of think of S as being L theta. The sort of axis is going to change, but then we can think of ds dt. Let's say S is distance that you moved along this curved line right here. So S is going to be measured in a circular way. S is a measure of arc length along the circle. ds dt is L d theta dt. And that's also equal to the velocity, because you're moving along this circle. So arc length, your change of arc length is actually your instantaneous velocity. So what all of that together implies is that we have that m of L of d theta dt is equal to negative mg sine theta. And we can see that sort of the mass of this object doesn't change the motion at all. The mass cancels out on both sides. So the equation that we get is that d theta dt. Sorry, I want to take acceleration is the second derivative. So it's I need to differentiate this once more. D squared theta dt squared. And then I'm going to bring this over and I'm going to divide by L. And then we have sine theta. Now, this is going to be a non-linear differential equation because if you sine of theta 1 plus theta 2 does not equal to sine of theta 1 plus sine of theta 2. So this is a non-linear. But what happens is when theta is small, we do the engineering approximation of saying that sine of theta is approximately equal to theta, because that's the first term in the Taylor expansion. And then the next term is third order. So up to second order, it's correct to say that sine theta is theta. So the small angle approximation is going to be that d squared theta dt squared plus g over L theta is equal to 0. And this gives solutions that theta is equal to, let's say, amplitude times cosine of the square roots of g over L t plus delta. So the period is approximately equal to 2 pi times square root L over G. So in other words, if you increase L by 4, then the period, the time it takes to do a full oscillation, goes up by 2. And then if you make gravity 4 times as strong, the period goes down by a factor of 2. Now, this is pretty accurate for small angles of theta. So, but the general solution is much worse, and you sort of have what are called elliptic integrals, and then you get a power series representation for what the period is. Okay, so that covers the case of this simple motion, which is unforced. So now we're going to consider case beta, which is going to be forced undamped motion. And this is going to be the equation x prime prime plus omega squared omega naught squared x is equal to f of t. And we are going to assume that f of t, so we're going to study this in the case of f of t is equal to f of sine then there's going to be some frequency here, which is going to be omega, which is different from omega naught, potentially. Plus, and then I'm going to call this beta. So in this case, we have two cases. Let's suppose that omega does not equal to omega naught. So we talked about the method of undetermined coefficients. And what we're going to do is let's just use an ansatz. And let's use the ansatz that x is equal to, let's say, a times sine omega t plus beta. And let's see if this ansatz is going to work in this equation, where a is just a constant. So I think it does. So if we take the derivative twice, well, it's sort of the usual behavior. We get a, then so omega squared, but sine, it becomes negative sine. So this is what happens when we plug x into the left-hand side. And then on the right-hand side, we have f sine omega t plus beta. And that works out. So what we get as a result is that a is equal to f over omega naught squared minus omega squared. And now if we sort of look at the solutions to the homogeneous equation, then they were cosine omega t. I guess I've done something inconsistent. I could have also chosen to make this cosine be a sine. That would also be an equivalent general solution because cosine and sine are just related by a phase shift. So we can also write that this is equal to c sine omega naught t plus delta prime, where delta prime is just related to delta by one of them being plus pi over 2 of the other. So let's write this solution in terms of signs just to be consistent. So what we're going to get is that x is equal to, let's say, some coefficients, let's say c. Then we're going to get sine of omega naught t plus delta. And then plus this particular solution plus f over omega naught squared minus of sine. And the frequency here is going to be difference. And in general, if you have sort of two sines and they have different frequencies, you most certainly cannot rewrite this as a single trigonometric function. So for example, you can sort of consider what the ratio of omega O to omega naught is, and that ratio might be irrational. And if that ratio is irrational, then this function will not be periodic, ever. Whereas if it is rational, it will be periodic, but it will have complex behavior. So if omega naught over omega is irrational, then X is not periodic. In the case that C does not equal to 0. But what it is that it's sort of a combination of two harmonic motions, and these harmonic motions you can think of as essentially being independent of each other. So that's how it works. Now, what happens if omega is equal to omega naught? That's a separate case. So what's going to happen is that basically trying to put this in won't work as our ansatz. So what we do is instead is we take this and we multiply it by t. Okay, let's think about it this way. So in general, a particular solution to the homogeneous equation, if we sort of combine these together, let's use this L'Hopital method. F of sine omega t plus beta. And then we can choose whatever C and whatever delta we want here whatsoever. So I'm going to choose C equals negative F. And then if I take the limits as omega naught goes to omega, then what this is going to equal by L'Hopital is F, and then I just take the derivative of this. And so it's going to be well, okay, cosine. So I can evaluate it at sort of any t I want. I'm going off of my notes right now. This isn't my notes, so I'm just thinking about how I do this. No, t, because I'm taking the derivative with respect to omega. So there's no derivative here. So it's going to be t cosine omega t plus beta. Divided by 2 omega naught. So the claim is going to be in the book, what I get is a minus sign out front. If I sort of think about this, if I take the limit as it's omega here, but it's omega naught here. So if omega naught is the variable I see, that checks out, because here I have omega and here I have omega naughts. So if I'm taking the derivative with respect to omega naughts, then it's actually going to be this term that's going to be affected. So it's cos omega naught t. Or you know what? Let's do it the other way around. Let's take the derivative, because sort of omega is fixed, omega goes to omega naughts. That's a bit more natural. So it's going to be the limits as omega goes to omega naughts. Let's write it like this. And then when I'm taking the derivative of this with respect to omega, it's going to be negative 2 omega. And then when I can evaluate this by setting omega equals to omega naughts. So then that's going to be negative f over 2 t cosine. There, that gets me the answer. Omega naught t. Plus beta. And you can check that this satisfies, this satisfies the differential equation. Thus, the general solution is going to be that x is equal to, let's say, some term c times sine of omega naught t plus delta, and then minus f over 2. Sorry, there's an omega here. Times t cosine omega naught t plus beta. And so what happens is that this term is going to range between negative c and c. Let's say ranges in. But for this term, we have this t factor. So what happens is as t gets big, when the cosine is close to 1, this term also gets big. This term can be big, let's say. Or rather, it oscillates between big numbers. Between increasingly big numbers. And what this is known as is resonance. And so the reason that this is important is that, for example, if you sort of, the classical example is that suppose you sort of have a bridge and then you have soldiers marching on it. And the soldiers, because they're trained to do so, march at some rhythm. And so you can imagine that their steps are going to be periodic. So the input forcing function is approximately going to be a periodic function. So let's say it looks like a sine function. Then there are going to be two things that happen. Let's imagine that the bridge is sort of like a spring. You can sort of imagine that it's sort of like maybe a suspension bridge, and then maybe it can move up and down like this, and then it sort of looks like a spring approximately. And so as associated to the bridge as a spring, there's going to be some frequency. And this frequency will be known as the resonant frequency of the bridge. And so what happens is if the soldiers march at any frequency that's not the resonant frequency, then what the differential equation will look like is there will be some coefficients here, C, but then it's going to be a sum of this, where notice, by the way, that when this is close to the resonant frequency, this term gets big, right? So there's going to be some term that just depends on what the initial conditions are. But ignoring that, the closer they march to the resonant frequency, the bigger this term gets, although it's still bounded. But if they march exactly at the resonant frequency, then what's going to happen is that as time goes on, the vibrations are going to become bigger and bigger, and this is going to cause the bridge to collapse. Because we have an out of control term, whereas here it was just an oscillation, which potentially got big if you got close to the resonant frequency. But when you're exactly at the resonant frequency, this term just blows up with time. And this is very important in engineering applications. They, for example, tell soldiers not to march in pace, not march. Well, march by definition means walk in pace. So don't march on a bridge, because if you march at the wrong frequency, then you can all die when the bridge collapses because you've reached the resonant frequency. And in London, for example, there was a very famous bridge that they built. And I don't remember what the name was. I think it was the Millennium Bridge. And what happened is that people sort of, when they started walking, the bridge started wobbling. And then people started adjusting their pace in which they were walking, which their bodies rocked from side to side, to match the frequency at which the bridge was beginning to oscillate. And so what that meant is that everyone basically started walking in step, and then the bridge started swaying a lot, and then they had to close the bridge for several months and figure out what the problem was. And there are like several videos on YouTube about this and how that sort of happens. Oh, so it's 7:01. Okay, so let's take a break until resume at 7:15, and then we'll do the other cases. See you then. Okay, so now on to case gamma, which is the case of free damped motion. And so what we have here is that x prime prime plus 2rx prime plus omega naught squared x is equal to 0. And so to give you an example of how something like this would arise, imagine that you have a wall, and then you have the ground, and then you have a spring attached to it. And then you have some weight right here. So what happens is that as this thing oscillates on the ground, there's also friction. And if we think about what friction is, then if the object is standing perfectly still, then friction isn't applying a force, right? If you're moving very slowly, there isn't that much friction. But on the other hand, if you're trying to slide very fast, there's a lot of resistance force. So what happens is that friction is proportional to the velocity of a moving object.
Isn't that like in honey or not like
like fluid viscosity? Well, for fluids, yeah, so you can say something about there's like the Bernoulli equation for fluids where viscosity comes in. So the analog of friction for fluids would be viscosity, right? Or something like that.
I was saying I think friction is only proportional to speed in like a thick liquid.
Well, it's also true if you're talking about friction along a block sliding along the ground. That's true as well. What would you say that it is?
No, because the force of friction is like constant. Oh, it matters.
If the object is standing still, then there's no friction, because friction opposes motion, right? And so if there's no motion, there's no friction.
No, I'm saying like if it's moving, then there's always the same friction or force.
Well, then it has to be discontinuous.
Yeah, with static.
That means that if it's standing still at 0 and then it suddenly jumps to, but that doesn't really make sense, because then what would happen is, imagine this is a differential equation. It starts moving a bit, and then so long as it's not actually constant, the force like overwhelmingly pushes it in the other direction. Let's imagine that it just hops over, that would start oscillating more and more, and then it would go out of control if sort of the force of friction was much bigger than the force moving the object. So imagine that there's sort of like you're pushing the object by like a very small force, right? Then imagine that friction were constant. Imagine that as soon as you started pushing the object, there was a massive force against you, then it would overwhelm the force by which you're pushing the object, and the object would actually slide the other direction.
No, I think, I guess the way they teach it is that there's the force is equal to how much you pull until this like threshold, and then after that there's just constant force backwards.
Okay, sure. I can believe that, but at small force approximations is proportional to the velocity of the object, right?
Oh, okay. Yeah, so I guess that sort of makes sense.
So friction F is let's say gamma. Gamma is, it's going to oppose the motion. So dx dt. And so what that would do is it would introduce this term, sort of, it's negative if we imagine gamma as being positive. And then when we bring it over, because the forces are on this side and they're negative, we'd sort of get a 2r coefficient with r greater than 0. That's sort of important. Because r is greater than 0 means that friction opposes motion. Now, as for the relationship to gamma to R, whatever. So it's going to be like there's going to be a mass factor and then there's going to be a factor of 2. The point is that the equation is nice when it has 2R in it. So we're going to analyze the equation of this form. But in practice, we're now talking about damped motion and damping forces. That's like friction. That's the prototypical one, right? Okay, so let's see what happens. So this is a homogeneous equation. And so we have the characteristic equation, which is going to be lambda squared plus 2 lambda r, but 2r lambda, let's say, plus omega naughts squared. Yeah, yes, that is equal to 0. And so what happens is the discriminant of this polynomial is b squared minus 4ac. So 4r squared minus 4 omega naught squared. So this is why we have the 2r here. And so basically what we have is cases. We have the case that R is greater than omega naughts. And so how you can think about this is that omega naughts is sort of going to be like the force of the spring. That's proportional to the spring coefficient. So if it's a very stiff spring, then it wants to retract a lot, right? But what happens is the stiffer the spring is, the quicker it's going to vibrate. If the spring is barely stiff at all, then it's flying barely any force and it's going to cause very little motion. But what happens is now we have friction. So in the regime where R is greater than omega naught, friction dominates the spring. And so friction is going to win over. And we're going to see that the solutions then, if R is greater than omega naught, what happens is that the solutions are real. So distinct real solutions. And basically, the two prototypical solutions are going to be x1 is equal to, so when we take the square root, it's going to be negative b over 2a. And so that's going to just be, so lambda so of r squared minus omega naught squared. I guess this is something that applies to the case where we have distinct roots. I'd write it differently if they were indistinct roots. And so what happens is that this quantity, omega naught is going to subtract from r squared, right? So this quantity is less than r. So in other words, lambda is negative. Right? So both roots are going to be negative. And so what we get is that x is equal to, let's say, a e to the negative r plus square root r squared minus omega naught squared plus b e to the negative, this is all multiplied by t. And what happens then is that in general, if a and b are the same sign, then it'll be a sum of two decaying exponentials. So these are decaying exponentials. Now, the possible pictures that you can get basically look like this. If both exponentials have the same sign, then it's just going to look at like from t greater than 0, just a decaying exponential. If the exponentials have an opposite sign, they can also look like that, but it's also possible to have the case where one of them wins over for small t while the other one wins over for large t. And what that sort of looks like is you start, I guess, somewhere, and then you have exactly one oscillation, and then it decays exponentially. And then it never crosses again. That looks like it's going up. I'll redraw that. So you can have 0 or 1 crossing of the x-axis. No more. Right. So this is not a periodic motion. And it's not an oscillatory motion either. Sort of it can rebound at most once, but then it decays exponential. So this looks like exponential. Decaying. Now, what happens if R is equal to omega naught? Then what happens is we have a repeated roots, right? And the way that we handle repeated roots are that, well, first off, lambda is going to be, this expression here is going to be 0. So it's just going to be negative R. And then x is going to equal a times e to the negative RT, and b times t times e to the negative RT. But what happens is that if we sort of look at this term, it gets multiplied by t. So maybe that makes the term bigger, but then there's an exponential. And exponentials always win over polynomials. So in other words, this is going still a decaying term. Now, I think that's the fact that there's a t there means that it's actually possible for the graph to cross the y-axis twice. So I think the highest number, sorry, of x-axis crossings possible is 2. I wrote them as numbers last time too. We can also sort of solve for this equation equals to 0. So we can set this equal to 0 and then we can prove it. But the point is that it's a bit more interesting than just two decaying exponentials. But it's not that much more interesting because it's still an exponentially decaying term because the exponential really wins over the polynomial. So in these regimes, basically friction is winning over the spring. And in this case, friction still wins over the spring. It still doesn't oscillate back and forth. It really just does at most 2 crossings and then decays. However, the interesting case is R is less than omega naught. And this case is known as the critically damped case. So what's going to happen here is that the roots are going to be imaginary. So lambda is going to equal negative R plus or minus I. And then we're going to have the root in the other way. So omega naught squared minus R squared. Now, if we look at this, then what we have is that X is A e to the negative RT cosine of square root omega naught squared minus R squared T plus B e to the negative RT sine. Square root omega naught squared minus R squared T. And so I think let's check what the names of this is. So what happens is that in this case, T is equal to 2 pi over omega naughts. Let's say T naughts is known as the natural period, the undamped period. Oh, by the way, let me just, before I do this, mention sort of the clear thing. And that's that you have A, B, and then the exponential is the same. So you can also rewrite this as C e to the negative RT times cosine or sine of square root omega naught squared minus R squared T plus delta. So by the same trick that we did before, it's a constant multiple e to the negative RT of A plus B, sine and cosine with the same period. And so we can recombine them. Then it's just, what does this look like? So what this looks like is that there's an exponential decay factor, right? But then there's also an oscillation. So in general, it's going to look like this. So let's draw sort of our exponential decay curves. Let's start them off somewhere big. So this is, let's say the curve e to the negative RT, and this is negative e to the negative RT. Then you're going to have an oscillation, and it's going to start wherever. And it's, so it doesn't have to start at its maximum. And so what it looks like is an oscillation that's decaying exponentially. But it's oscillating between two exponential decaying things, but it's going to cross the x-axis infinitely many times. And it's going to cross it periodically at a given, well, yeah. So T naught, which is 2 pi over omega naught, this is going to be the undamped period. Or natural period. And then T, which is 2 pi over the square roots of omega naught squared minus R squared. This is known as the damped period. So you can see that instead of dividing omega naughts, we're going to divide by a number that's smaller. And so we're going to get something bigger. And so the period is the amount of time that it takes to make an oscillation. And so the oscillations slow down. So in the presence of friction, what happens is that you get oscillatory motion that's decaying exponentially, and the period is going to be longer than the period that you would have had without friction. But okay, and so now we get into the most interesting case, which is delta, which is forced. Did I capitalize these things? Yep. So our equation is x prime prime plus 2rx prime plus omega naught squared x is equal to f of t, where we're going to assume f of t is equal to f sine omega t plus beta. So it's going to be the same forcing function that we saw before. I mean, in general, you get the full complexity of second order inhomogeneous equations, which you solve by variation of parameters. But it's going to be interesting to analyze what happens in this sort of periodic motion, periodic forcing function case. And so, like the example that I gave of the periodic forcing function would be soldiers marching on a bridge in a periodic way. So let's see if the bridge has resistance, then to what extent is the bridge going to be strained, and is it going to collapse? So that's the question. Now, what's going to happen is that sort of if we're going to use the ansatz, that x is equal to a times, I'm going to put sine first. And b times cosine. So if then what I'm going to get is, when I differentiate, I guess for the sine term, it's going to be a omega negative a, okay, a times negative omega squared. It's not that perfect. Okay, I'll just do term by term. Negative omega squared a sine omega t plus beta. Then the derivative of sine is cosine, so plus a plus omega a cosine omega t plus beta plus a sine omega t plus beta. And then if I do these cosine terms, I'm going to get minus omega squared b cosine omega t plus beta. Then when I differentiate, once cosine is negative sine. So overall, what that's equal to is, if I group it with the sine terms, which is sort of what I care about, it's negative omega squared a minus omega b plus a sine omega t plus beta. And here I'm going to have minus omega squared b plus omega a plus b cosine omega t plus beta. And what I want that to equal is f sine omega t plus beta. So this is a 2x2 linear system for A and B. And what I'm going to have then is that sort of if I imagine A and B, this is 1 minus omega squared. I can rewrite it like that. So 1 minus omega squared, then minus omega, then for the A coefficient is going to be omega, and then 1 minus omega squared times AB. That should equal, so on the first one, where I have 1 minus omega squared A minus omega B, that should equal F. And this should equal 0, right? So what we get then is that AB is equal to 1 over, so this would be 1 minus 2 omega squared plus omega to the 4th. And then what we'd have is we'd add on omega squared. Wait a second. Right. Sadness. This is 2r. And this is omega squared, omega naught squared. So the ones are actually omega naught squareds. And these are actually 2r omega. So that actually makes it nicer. What happens is that I have omega naughts to the 4th minus 2 omega squared omega naught squared plus omega to the 4th. But then what happens is that I add 4 omega squared omega naught squared. And what that does is it changes the omega naught squared minus omega squared to being, well, it's going to be omega naught squared plus omega squared. Wait a second. No, there's also a there's an entire r squared here as well. Right, so actually, I'm not going to expand that out. Sorry, I thought that expanding that out might be good, but it's not actually good to expand it out. We get 1 over, omega naught squared minus omega, squared, plus, 2r omega, squared. So I'm going to write it like that. Then this matrix becomes omega naught squared minus omega squared. So that, and then we put minus signs here. So what happens is it's just this column that's picked out. So that tells us that A is equal to F omega naught squared minus omega squared divided by omega naught squared minus omega squared plus 2r omega squared. And B is going to equal yeah, no, that's right. Minus 2r F. Oh, or minus F2r omega. Divided by the same denominator. So the key about this is that sort of we have this term squared at the bottom and then this term squared at the bottom. So what happens is if we factor out F, A, B live on the unit circle up to the factor of F, right? So setting okay, sure. You know what? Let's set cosine. Let's set sine of alpha equals to this expression. Without the F. If we set sine of alpha equal this, and we set cosine beta is this without the minus sign, so that's going to be better. Cosine alpha is equal to this without the minus sign. Or perhaps I want so A is going to equal sine. So it's going to be sine. Okay, you know what? No, I'm going to set this cosine and this to sine. So what I get overall is that x by my ansatz is equal to cosine al, oh, so I should remove the F here and I want to remove the negative sign as well. So I get cosine alpha times sine omega t plus beta. F times minus sine alpha cosine omega t rather plus beta. Yeah. And what that's equal to is F of sine of omega t plus beta minus alpha. So you can check that. Of course, there's also sorry, I made another mistake. I want to right. In order to normalize this, I would like to have square roots here. And so if I have square roots here, then what I no, sorry, A and B are the what we had before. I'm going to set A is this. So to normalize it, I actually need to divide by square roots. And then I have a floating square root out front. Yeah, okay, that's what it is. This expression, which is equal to F over square roots omega naught squared minus omega squared plus 2r omega squared times sine of omega t plus beta minus alpha. Okay, so this is our final expression for the inhomogeneous part, where alpha is defined in terms of those previous two equations. So this agrees with what's in the book. And so the general solution is going to be this plus the solution to the homogeneous part. Now, the solution to the homogeneous part is sort of going to depend on what case we're in, right? Because we can have R is greater than omega, R is equal to omega, or R is less than omega naught. And in each one of those cases, we'll get some specific solutions to the homogeneous thing, but independently of all three of those cases, the solution to the particular solution is going to look like this. So the solutions to the homogeneous equation depends on R, let's say, greater than or equal to or less than question mark omega naughts. But the particular solution doesn't depend on that. The particular solution is always this. So how are we going to interpret that? Well, what happens is that, notice that basically in the previous case, this decayed exponentially, this decayed exponentially, and this decayed exponentially as well. So what happens is that the particular solution is going to become, so the solution to the inhomogeneous part, no matter what it is, what solutions you add, it's going to become irrelevant at a certain point in time because it's going to decay and it's going to become very small. So what remains is this, and this is known as the steady state motion. So independent of the case, the homogeneous part decays exponentially. Whether or not it oscillates, it still decays exponentially. But the steady state solution is going to be a constant periodic solution. So what we see then is that the periods of the steady state solution is going to be omega. It's going to be the same frequency as the driving force. So the steady state solution has period 2 pi over omega. And what we see then is we have this expression at the bottom, the amplitude is, so of the steady state solution, is going to be F divided by the square roots of omega naught squared minus omega squared, squared, and then plus 2r omega squared. So what we see is that basically if we are fiddling with, if r is fixed and we're fiddling with omega,
So there's like a new resonant frequency because it doesn't, if omega is equal to W0, then maybe it has a high 2RW squared.
So let's just look at this denominator expression. And let's try and make the denominator, because to make the amplitude as big as possible, we want to make the denominator as small as possible, right? So let's say omega naught is fixed. And let's consider, let's say g of omega is equal to omega naught squared minus omega squared plus 2r omega squared. So this is a quartic equation in omega, but g prime is going to equal, so if we do chain rule, we're going to get 2 omega
Minus 2.
It can be minus 2, but then we're going to get minus here. So the minuses cancel out. But it's going to be 4 because we have 4 omega. I think this is right. If it was, because obviously this expression is the same if it's omega squared minus omega naught squared. So if it were omega squared minus omega naught squared, if it was omega squared minus omega naught squared, then that would be better. So it's actually omega squared minus omega naught squared, I think. In that case, the signs work out, right? Then it's all positive. Then the chain rule derivative would be 2 omega squared. We'd have 2, and then we'd have this term. And then here we have plus 4r squared omega squared. So when we differentiate that, we're going to get plus 8r squared omega. Yeah. So G prime omega is equal to 0 when, so divide by omega everywhere, divide by 4, when 0 is equal to omega squared minus omega naught squared. Plus 2r squared, right? So in other words, omega is equal to plus or minus the square root of omega naught squared minus 2r squared. And this is assuming that omega naught squared is greater than 2r squared. Okay, so if this happens, otherwise there is going to be no maximum denominator.
Could we
No
check?
minimum. Go ahead.
Oh, okay.
So assuming that we're in this regime, then what happens is if we set so here the expression omega naught minus omega squared appears. So this also tells us that omega naught squared, omega squared minus omega naught, or the other way around, is equal to 2r squared, right? So what we get then is f max is equal to f, or rather a max, let's call it amplitude max, is equal to f divided by, then what we'd have is that this expression becomes 2r squared, so square root 2r squared. And then we have plus 4r squared omega squared. Oh, because this is squared. So it's actually 2r squared squared. There we go. Yeah. So 4r to the 4th. And what we get then is that this is F. We can factor out the 2R from all of this. And omega here is equal to omega naught. This is also not good, because I get here the book has a minus sign. Oh, I see. 2R omega. No. Okay, this makes sense. This does make sense. So what we have is F divided by the square roots of omega naught minus omega squared, which is 2R squared. So 4R to the fourth. Plus 4R squared omega. And then omega squared. Omega squared is equal to omega naught squared minus 2R squared, right? So what we get overall is F over so so the 4 this becomes an 8. So we get square root of 4R squared omega naught squared minus 4 times R to the fourth. And so what that becomes finally is F over 2R times the square root of omega naught squared minus R squared. And this happens again in the case where omega naught is greater than 2R squared. So omega naught squared that is but it will only happen if we have this stronger case as well. So what do we discover? We discover that the maximum occurs at a different thing. So the resonant frequency is different. But the resonant frequency will not make it happen so that it goes to infinity, because it's still a bounded motion. So you still have a maximum amplitude, right? But the maximum amplitude you can see as R becomes close to omega naughts. So if wait, does this make sense? Oh, yes. If R becomes very small, then this blows up, right? Because I'm dividing by R. So as R goes to 0, A max goes to infinity. But the point is that so long as R is greater than 0, A max is finite. So what happens in the case of a force damped motion is that there's an exponentially decaying set of solutions to the homogeneous equation, but then there's a steady state motion, which is periodic. And eventually, as time gets big, it just converges to this periodic motion because the other terms decayed exponentially and don't matter. Now, what is the amplitude of this motion? We found that the amplitude is given by this expression, and the amplitude is maximum when omega is going to be either one of these cases. And sort of, if you think about it, then the difference is, let's see how omega appears. If we have sine negative omega, that actually flips the sign. But you can sort of imagine beta changing by pi. And if beta changes by pi, then the sign does get flipped. So you can imagine that omega is positive without loss of generality by just changing beta to be a different value. So assuming that omega is greater than 0,
or you could
both
imagine
of those cases. Go ahead.
Time going backwards.
Yes, but also just changing beta would also count for that. Sort of the exponentially decay, because this doesn't matter to the behavior of the exponentially decaying terms. So the exponentially terms don't become undecaying if you change the sign of omega. That only changes the steady state solution. And the steady state solution, it doesn't decay exponentially, it just remains at a oscillation at a constant amplitude. So I think that both of these are going to be minima. It's a 4th-order polynomial, and so overall it's going to look like a quartic, but then it's going to look like this essentially. So there are going to be 2 minimum solution at both of these values. That's what it's going to look like. But at either one, so if we assume that omega is positive, then we can take the positive root without loss of generality. And so the resonant frequency is this. This is the new resonant frequency. Rather, this is the damped resonant frequency. And if you look at what the resonant frequency is, then forget about the sign. Originally, it was omega naught squared, but now we're subtracting 2r squared. So the resonant, well, rather, this is omega. The resonant frequency is 2 pi divided by omega. So what we're going to do is we're going to divide by a number, or rather the period. Anyway, omega becomes smaller case for resonant frequency, and then the periods becomes so you're dividing by a smaller number, it becomes a bigger period. So in order to have resonance, you have to have a slower period in your damping function overall. Yeah. But then you can see that you're still in danger, because if the damping function is small, then A max is going to be very big. So if R is pretty small, then the bridge will still collapse because this will still get very big. But sort of if R is big enough, then you can sort of guarantee that the bridge won't collapse if you're at the resonance, damped resonant frequency. So that sort of completes, it's the analysis of all possible cases where the damping function is an oscillation. This is going to be relevant sort of for the electric case, because the electric driving force is either going to be constant or it's going to be periodic in the case of, for example, a alternating currents. So it's 8:15, so I'm not going to take a break. I'm going to go on for a bit longer. I'm not going to cover, I'm going to, so we'll see when I'm going to end. Okay, so electric circuits. By the way, so where would you have a forcing function? Well, you all much more obviously have a forcing function in electric circuits, But you sort of have a pendulum, and sort of the frame of the pendulum is also moving, and that would be like a forcing function. Okay, so let's say we have a circuit. The circuit looks like this. So there's going to be some energy source, E. And then what's going to happen is that there is going to be some resistor. This is how you apparently draw a resistor. And then there's going to be some induction coil. This is known not as an induction coil, but as a inductor. And then there's going to be some capacitor, which is drawn like this. So the capacitor is going to be measured in terms of, what are the units? So this is going to have some resistance R. This is going to have some inductance L, and this is going to have some capacitance C. So R is measured, well, E is measured in volts. And this is known as the electromotive force of the circuit. R is measured in ohms. And then C is L is measured in henries. And C is measured in farads. And what there is implicitly here is that there's also going to be a current in the circuits. And the currents, which is unfortunately denoted by an I, it's not the imaginary unit, it's the currents, is measured in amps. And so how electric circuits work is that basically it doesn't make sense to measure voltage in absolute units by an instrument, but it makes sense to measure voltage as a difference. So basically you can take a voltmeter and you can connect the voltmeter here and here. And let's say this is your voltmeter. And what it does is it measures the voltage change from here to here. You can think of voltage as sort of a potential energy thing. And the difference between the potentials is meaningful. So the way that sort of batteries or electromotive things work is that the voltage drop between them is defined as being whatever the value of E is. So no matter what, the voltage difference between here and here is going to be E. Now, what happens for everything else is that the voltage is going to be measured as some function of the currents, the voltage drop. So you can sort of think of E as an energy source. And the rest of the things, as energy sinks. measured by the voltage drop across the components. So a resistor is, you can just think of it like that. It resists electric flow. If you're trying to flow past a resistor, it's hard. Now, what an inductor is basically if you have electricity traveling in a loop, then it's going to create a magnetic field transverse to the thing. And magnetic fields store energy. So magnetic fields have an energy. So I would sort of call this B, the magnetic fields. And what happens is B stores energy. So if the current changes, then the amount of energy stored in the magnetic field changes as well. So what L does is that it resists changes in currents, because as the current changes, it has to store more energy in the magnetic fields. So you can think of R resists currents. And then sort of L is going to resist changes in currents. And now how a capacitor works is that it's literally sort of breaks the circuits. These two sides of the capacitor are not connected. But the thing is that they're very big. So as the current flows, this can accumulate a large positive charge and this can accumulate a large negative charge. And overall, it's going to be neutral. So what a capacitor usually looks like is you take two sheets of metal conducting material, you put an insulating sheet between them, and then you roll it up. What happens is sort of the capacitance has a limit. There's limits to how much charge it can store safely. But as the difference gets very big between the two charges, it's going to be much harder to add more charge onto these things. So C makes it harder to accumulate charge as the charge gets bigger. And all of these are associated with a certain voltage drop across them. So the formulas are that sort of delta V of a resistor is equal to so the voltage drop is equal to the resistance times the currents. Now for a capacitor, what we have is that the voltage drop, for an inductor, is equal to the inductance times the change in currents. So if the current is constant, then it'll just flow and the magnetic field will be steady and there's going to be no voltage drop. It's just going to behave like a straight wire. But if the current is changing, then the magnetic field is sort of absorbing or releasing energy, and that's going to create a voltage drop as that happens. And for a capacitor, that's the voltage drop is going to be 1 over C times the stored charge, where had the stored charge is related to the currents. So what we have is that's basically dq, that's rate of change of the charge over time, is equal to the currents. And one way to write this equation would be by saying that basically, so you can sort of think of this as another way to write this is V equals Ri for the first one. For the second one, you can say V is equal to, or rather, let's say Ri equals V. Then you can write L di dt. You know what? No, let's we'll write V equals Ri. Then you can write L times di dt is equal to V. Whereas here, what you have is that C times dv dt. Is equal to I. So you get that by differentiating this equation, right? And so you can see that there's sort of a duality between inductors and capacitors given by these equations. These are sort of dual. Now, what's going to happen then is that we have Kirchhoff's voltage law. And that basically says that in a loop, all of the differences of voltage have to basically, if there's a potential difference, then the potentials have to make sense as a function. There actually has to be a potential function which solves all of these differences. So the voltage changes in a loop. Sum to 0. And that's because sort of voltage is a potential and you sort of can't, the potential exists. Because the potential exists, the changes in potential in a loop have to be constant. Sorry, sum to 0. But what this means is that there's going to be a potential drop across all of these elements, but then there's going to be a potential increase across E. So what that says is basically that E is equal to the sum of the drops. And the sum of the drops is going to be Ri. And this is only in the case of this circuit where we have a resistor, an inductor, and a capacitor connected in series. In general, you might have maybe 2 resistors, or you might have some of these components missing. But if you have all of these components, then the voltage drop is going to be this, plus the voltage drop across here. Plus 1 over C cubed. Now, we want to express this in terms of I, so we differentiate this. So then what we get is that dE dt is equal to, and now we can rearrange it to L d squared I dt squared. Or you know what, let's write it in the usual differential equation form. Then we're going to get plus R di dt plus 1 over C I, because that's the time derivative, and that's equal to dE dt. And this is a second order differential equation. Linear. ODE. And so basically we've just analyzed this equation a second ago. If we divide through by L, then we're going to sort of get it in the standard form, right? So we just studied this equation a lot. And then we can say what all of the solutions are going to be, and we basically know about the cases. And then I can sort of do some cases. Let's imagine that if E, let's see, what time is it? It's 8:31. Okay, I will just say this. If E of t is equal to F omega times cosine omega t plus beta. So I've multiplied F by omega. Then you get very bad expressions. They're big expressions. Then I'll just write down what the answer is. The current is going to equal, so there's going to be some amplitude, let's say C, times E. And this is sort of assuming complex solutions. Complex roots. So probably the condition is that this radical is positive. So this is going to be sort of the transient solution that's going to decay exponentially, and then there's going to be a steady state solution. Where alpha is defined by some analogous equation, this depending on stuff. So anyway, we've seen this before. So in if not complex roots, then this is going to change, but the steady state solution isn't going to change. The steady state solution is going to look like that in this case. Now what we're going to do next time is something more interesting. Okay, there's apparently some analysis that you can do here. So the amplitude is going to equal this expression in the steady state case. And what you're going to do is that this denominator is called the impedance of the circuit. I guess if we divide by C on top and bottom, then what we have is that the amplitude for Z is equal to the square root of R squared omega squared. Oh, there's an omega. So if we divide by omega C, then we're just going to get R squared plus 1 over omega C minus L omega squared. And the amplitude is proportional to this. So the amplitude is inversely proportional to this. Is the impedance of the circuit. And the steady states. Amplitude of the currents is inversely proportional. So this calculation is boring, and this term would depend on quadratic things, but this term would always exist at this steady state independent of what's the solutions to the quadratic are, whether they're real, imaginary, or doubles. And we see that the amplitude of the currents to the steady state is going to oscillate. It's going to be this function, 1 over z. So it's going to be f over z. Okay, and I think that that's where I'm going to end for today. Next time, we're going to start off with stuff like, I'll give an example. So in the simplest example, we're going to have something like E. And then we might have a resistor here. And then the circuit might split into, let's say, another resistor here. And then let's say the circuit splits into 2, and then we have an inductor here. And then let's say we have a capacitor here. And let's say we have another capacitor here. And so what's going to happen is that there's going to be a current I here. Then this is going to split off into 2 currents, I1 and I2. And then we're going to have Kirchhoff's current law, sum of the incoming things equals the sum of the outgoing currents. And then this is going to give us a system of differential equations to be able to solve for all of the currents in this circuit. Okay, anyway, so today what we learned was what second order sort of equations which would be forced by an oscillatory function, and all of the possible cases that we can have and how they apply to things like springs, pendulums, and then springs motion that's driven by a periodic force. And then the case of how resonance works, where in one case it makes it blow up, but in the other case it's sort of bounded, but you have a 1 over r thing. So if the damping becomes small, then it still gets very big. And then a bit about circuits and how circuits give rise to basically the exact same equations that you'd see if you had a spring system that was damped. So this is the same type of equation. You can translate between springs with damped motion and forcing function to circuits like this. There's a one-to-one translation. So instead of talking about springs, we can just think about things like this. And that just gives the coefficients of a second order constant coefficient linear differential equation, and then the damping thing is this. Okay, cool. Any questions? Right. So I set the homework deadline to be tomorrow at midnight. You can submit it a bit late if you want. Hopefully all of the midterms should be in by now. Okay, anyway, see you on Wednesday. Bye.